So far we have discussed quite a bit about the concept of equilibrium and equilibrium constant and discussed a few examples of these concepts. As I mentioned earlier, equilibrium and equilibrium constant and associated thermodynamic quantities offer a lot of applications in the discussion of the processes both qualitatively and quantitatively. In biological systems, we are very much concerned about the pH. How to select a suitable combination of salts to prepare a specific pH solution. So, in order to understand these things in more details, let us today discuss about the acid base titrations and how we can apply the discussion on equilibrium and equilibrium constant to address acid base titrations. Acidity constants we have discussed in our earlier lectures what is acidity constant and how to write an expression for the acidity constant. Acidity constants are very useful in deciding the value of the pH that signals the stoichiometric point. In an acid base titration, stoichiometric point is also called equivalence point. We remember your school laboratory, you were using a burette and a flask to titrate an acid with a base and trying to find out the end point by using an indicator. And that end point I am referring to as stoichiometric point or equivalence point. Let us discuss a few things in detail. Let us first consider, let us look at the slide. We consider titration of a strong acid with a strong base. An example of strong acid is HCl. We discussed in the previous lecture that an acid which is virtually completely ionized in solution, we call it as a strong acid. And a strong base, again an example is sodium hydroxide, which is virtually completely ionized in aqueous solution. Let us consider the titration of a strong acid with a strong base. And let us take a look at the slides. Cations from strong base, for example, sodium ions from sodium hydroxide and anions from strong acid, for example, chloride ion from HCl, barely affect pH. Then the solution contains these ions. What are these ions? Sodium ions, chloride ions, water, H3O plus and OH minus ions from autoprotolysis of water. Let us recognize that when you are titrating an acid with a base, you have the ions coming out from the acid, you have the ions coming out from the base and you also have ions which can come out from the autoprotolysis of water. Now, it is a different matter that whether the amount of hydronium ion and hydroxide ions produced from the autoprotolysis of water can be ignored or not. That we will discuss. And let us go back to the slide. Autoprotolysis stoichiometry in this case guarantees that pH is equal to POH. That means, when we are titrating a strong acid with a strong base at equivalence point, pH will be equal to POH, and that means if pH is equal to POH, that means pH we are talking about is equal to 7 at the stoichiometric point. And as I said, the stoichiometric point I am referring to as equivalence point. Okay, let us talk about now titration of a weak acid with a strong base. A weak acid, again as we discussed in the previous lecture, is not completely ionized. It is very weakly ionized. And an example of a weak acid is acetic acid. A strong base which is virtually completely ionized. So, let us take this example and go to the slide. Weak acid, example is acetic acid. So, when you titrate, what you have, let us write down the equation. We have CH3 COOH aqueous plus NaOH, it will produce CH3 COONA plus H2O. So, the solution upon titration forms sodium acetate. Let us remember, since we will be connecting our discussion with the equilibrium constant, and eventually equilibrium constant is connected with the Gibbs energy. If we are talking about the titration of a strong acid with a strong base, the product which is formed, because the reaction, the ions are virtually the whatever the acid or alkali base which we are taking, if it is strong, that is virtually completely ionized. That means, in that case the minima in the Gibbs energy versus extent of reaction will lie close to the formation of products. And when it is weak acid and strong base, and weak acid is not completely ionized, that means we are talking about minima which is lying close to the reactants. Coming back to the titration of a weak acid with a strong base like sodium hydroxide, which is a strong base, and acetic acid, which is a weak acid, the analyte solution becomes sodium acetate. So, what does the solution have? As I just discussed, it will have acetate ion, it will have sodium ions, and of course, always you will have ions from autoprotolysis of water. So, let us go back to this. This is the weak acid, and its conjugate base, if I write, this is the weak acid and its conjugate base is acetate ion CH3COO minus. This is its conjugate base. So, due to this Bronsted base, we can expect the pH to be greater than 7. When we titrate weak acid with a strong base, CH3COO minus is a Bronsted base, it can accept a proton, and therefore, we can expect the solution to have a pH which is greater than 7, because pH greater than 7 is supposed to be an alkaline solution. that is in which there is an excess of the base. So, that is what is commented over here in the slide, that due to Bronsted base CH3COO minus, we can expect the pH to be greater than 7. This is the scenario when you titrate a weak acid with a strong base. Now, what about when you titrate a weak base such as ammonia with a strong acid such as HCl? And obviously, when you titrate ammonia with HCl in an aqueous solution, the analyte solution becomes ammonium chloride. In the solution, you will have formation of ammonium chloride. That is what is commented here. The analyte solution becomes ammonium chloride, and now the solution will have ammonium ion, will have chloride ion, and as usual the ions from the autoprotolysis of water. And what are those ions? These are hydronium ions and hydroxide ions. Ammonium ion, this is a Bronsted acid because it can donate a proton, and therefore, we can expect the pH to be less than 7 over here. So, look at the comment, due to the Bronsted acid NH4 plus, we can expect pH to be less than 7. We have taken examples of titration of a strong acid with a strong base, or titration of a weak acid with a strong base, or titration of a weak base with a strong acid, and discuss that at the equivalence point for the titration of a strong acid with a strong base, pH is expected to be 7, because you will have a neutrality at 25 degree centigrade over there. And when you titrate a weak acid with a strong base, we can expect the pH to be greater than 7 in the solution. And when you titrate weak base with a strong acid, you can expect the pH to be less than 7. What about generation of a complete pH curve? When you titrate an acid with a base, how will the complete pH curve against the volume of the acid or volume of the base titrated will look like? Let us discuss that. We will now discuss titration of complete pH curve. Let us assume that we titrate a volume Va of a solution of weak acid, and the concentration of weak acid let us take as A0 moles per liter. This is the analyte, and we want to titrate it with a strong base MOH. The molar concentration of strong base, let us call it as B. This is the titrant. So, what we are talking here is the titration of a volume Va of a solution of weak acid with a strong base. That means, you are taking a strong base, and to that you are adding Va centimeter cube of a weak acid, and then monitoring the changes. So, obviously, we are talking about an acid. What is the acid? Let us represent acid by Ha. This is our weak acid, and strong base we are representing by MOH. This is weak acid, and this is strong base. So, what we will have after these are titrated, what are we going to have in the solution? We are going to have M plus aqueous, we are going to have A minus aqueous, which will come from the ionization of Ha, and then we will have H3O aqueous, and we will also have OH minus aqueous. We are going to have these ionic species in their aqueous form in solution. Okay. The solution is electrically neutral. Let us go to the slide. Since the solution is electrically neutral, this equation will hold, that is the total positive charge will be equal to total negative charge. We write in terms of the concentrations of whatever positively charged species, sum of that has to be equal to the sum of the concentration of all the negatively charged species. The next step is to calculate or to find out the total number of A groups, or you can express in terms of amount also. A groups will come from Ha and A minus. Obviously, A is present in Ha, and whatever is its extent of ionization, since it is a weak acid, its extent of ionization is going to be small. So, A minus is also going to be there. This is equal to A naught into Va. How it comes? I will explain that. The initial concentration was A naught of the acid, and let us say I write this as mole per liter, and we add Va, I can express centimeter cube or liter, whatever volume. So, therefore, the total number of A groups is going to be, you multiply Va into A0, these many moles. That is the amount of A groups. And let us go to the slide. Total number of A groups is constant and is equal to A0 into whatever is the volume of the acid, weak acid added. And this has to be constant, whatever Ha plus A minus, this is equal to total number of A groups. But also let us realize that when you are adding A to strong base, when you are adding an acid to strong base, the total volume is also changing. Imagine the titration which you do in acid base. You are taking one solution in the flask and the other solution in the burette, and when you are adding a small amount of the solution from the burette into the flask, the total volume in flask is increasing. That means the concentrations are also getting modified. We have to take into account that. And let us look at the slide. The amount of A modified when you add A to B is equal to A0 into Va divided by Va plus Vb. How do you get that? You can get it by using, for example, if you remember, you were using this kind of equation, N1 V1 is equal to N2 V2. This must apply. So, if I use, initially it was A0 and we took Va centimeter cube of the acid, this has to be equal to, if the final amount is A and the total volume is V A plus V B. And from this, A is equal to A 0 into V A divided by V A plus V B. Once again, from here A is equal to A 0 into V A divided by V A plus V B, and that is what is written on the slide. A is equal to A 0 into V A over V A plus V B. Okay. If the concentration of the acid changes, the concentration of the M plus cations coming from the alkali, from the base, also changes. And exactly the similar calculations can be done, and the amount added at any stage is B times V B, and the total volume of solution, as I just discussed, is V A plus V B. And if I write M plus concentration, that is whatever is the amount of base that we are adding. Base is MOH, so M plus is coming from the base, and M plus is interacting with A minus to form the salt. So, therefore, this is equal to S. S is the salt concentration, and by the same arguments as we discussed for A, S will be equal to B times V B over V A plus V B. The points to be noted in this discussion is that we are writing M plus equal to S. S is the salt concentration of salt formed, which will be equal to the amount of cations given by the base, and this S is equal to B times V B or V A plus V B by the same arguments that we discussed earlier. And this quantity S denotes the current concentration of the salt, that is the product of the reaction. You are titrating a weak acid with a strong base. So, A minus will come from the acid and M plus will come from the base, will form a salt Ma, and S denotes the concentration of that salt formed, which is the product of the reaction. All right. Now, let us write an expression for the autoprotolysis constant, that is Ka. Now, let us write an equation for the acidity constant Ka. We always write Ka as activity of hydronium ion into activity of A minus divided by activity of Ha. And now, let me assume the activities to be close to concentrations, that is, I am assuming that the solution is very dilute. Then let me write another equation for the autoprotolysis constant of water, that is Kw, which is also activity of hydronium ion into activity of hydroxide ion. So, let me also assume that the activities can be replaced by the concentrations, assuming that there is lot of water. Then, if I combine these two equations, I can write another expression for A minus, and this comes from the conservation of A groups. The conservation of A groups, remember that if I go to one of the previous slides, I was writing Ha plus A minus is equal to A. So, by using these equations, I can get an expression for A minus in terms of the acidity constant, and in place of hydronium ion concentration, allow me to write only H. H means H is the hydronium ion concentration. So, once we have obtained this relation, next we can use the electrical neutrality condition in terms of H alone. What we are doing is we express electrical neutrality condition in terms of H alone. And what is that condition? This one, solution is electrically neutral, that is the total concentration of positively charged species is equal to total concentration of negatively charged species. We have an expression of M plus A minus and OH minus. For example, we have A minus here in terms of the acidity constant and hydronium ion concentration. For M plus and for A minus I have discussed, A minus is A times Ka over Ka plus H, and OH can be from here in this expression I can write in terms of Kw divided by H, and M plus can come from the previous discussion. Let me just go back and show you. M plus is equal to S, and S also in terms of Vb and Va can be written. Once we combine all these concentrations for M plus, A minus and OH minus and H3O plus I write as H, I get this kind of equation. Now, this kind of equation is quite cumbersome kind of equation, which will actually, if you try to rearrange, it will come as a cubic kind of equation. And to solve this equation, for example, if we look at, let us go back, if we look at this equation, solving this equation is not that easy. One may need a computer to solve this kind of equation. So, let me rearrange that equation, and I can write that equation in terms of Vb and Va, because when you titrate, you know the volume of the alkali added and you know the volume of the acid taken, and these volumes can be connected with H. And now you try to solve. Again, here you see it is third power of H. So, therefore, you will need definitely computer to solve this equation. But nevertheless, we will discuss that what approximations can be made, but the complete pH curve for various values of pK, these are pKa values, for various pKa values will look like this. So, you see the pH will be expressed in terms of hydronium ion concentration. For various Vb and Va, you get hydronium ion concentration for different Ka values, and those hydronium ion concentrations can be expressed in terms of pH, and then you generate these kind of pH versus Vb by Va titration curve, and for different pK values you see how the pH will vary. So, this is the complete pH curve as a function of the volume of alkali or volume of acid added to the alkali. So, this equation enables us to find the volume of base needed to achieve any pH. Since it is against Vb by Va, you are varying B, how much base is needed to achieve any pH can be obtained by this equation. As I mentioned earlier, that though this equation is very general, it is not very easy to use without a computer, because H into H square, that becomes third power of H. Main features of the curve we can identify by making a series of approximations. And what are those series of approximation? The approximations that we will use, since acid is weak, therefore HA is more abundant than A ions in solution. HA is weak acid is very weakly dissociated. Therefore, the amount of A minus ions will be very less compared to HA. And when HA is present, it provides hydronium ions that greatly outnumber any that stem from autoprotolysis of water. This is also assumption, that means we will be ignoring the hydronium ions which are coming from autoprotolysis of water, and we will be considering hydronium ions that will come from HA. And when excess base is present, the OH ions which come from the base will dominate any that come from autoprotolysis of water. These are the approximations that we are going to make. So, after addition of some base, that is before the stoichiometric point is reached, the concentration of A minus ions will come almost entirely from the salt, as the acid is very weakly dissociated. So, you have HA which will form which will give A ion, and then you have A ion which will stem almost entirely from the salt which is present, which is formed as a product. So, we will assume that after addition of some base, the concentration of A ions will come entirely from the salt, because acid is weakly dissociated. Therefore, I can approximate A minus equal to S, that is the concentration of salt, and therefore, the molar concentration of acid, new molar concentration of acid will be A whatever it was minus the S is the concentration of the salt. So, instead of A, now I will use the molar concentration of acid HA as A prime, and therefore, you write the acidity constant as usual, and instead of A minus activity I will use S. That is what I am saying, I am approximating A as S, and instead of AHA I will write A prime. And now when you convert this into pH or pKa terms, you take a logarithm on both sides and write pK as minus log Ka and pH as minus log activity of hydronium ions, you will get this expression, pH is equal to pKa minus log A prime by S. A very important equation, this is called Henderson-Hasselbatch equation, which in other words, in other terms it is written as pH is equal to pKa minus log concentration of acid divided by the concentration of base. This is a very important equation, we will discuss more about this in the next lecture, but now if I take A prime equal to S, that is when the concentration of acid is equal to concentration of salt, then pH is equal to pKa. So, that means pKa of the acid can be measured directly from the pH of the mixture. See, if we know the pH, if we know the concentration of A, that is acid, and S, that is salt, we can measure pKa. So, the discussion in this lecture has led to generation or the discussion on the generation of the complete pH curve and the derivation of a very important equation, the Henderson-Hasselbatch equation. We will discuss more about the Henderson-Hasselbatch equation in the next lecture. Thank you very much.